So it's going to be the 5th lecture today. It's nice, my slides say the date as well, which is nice. Today we'll talk about the differencing schemes. So we talked about the equations the other day, and then when you have written the equations, you have discretized the equation and solve it numerically. So these are the numerical schemes that we use in CFD, and we'll talk about the finite difference and finite volume methods, and first, second, and third order schemes for numerical solutions for the partial differential equations. The partial differential equations are the governing equations that we did the other day. So Navier-Stokes equations and so on. And then we are approximating those partial differential equations with a numerical scheme. So, so once you have written the so this is your Navier-Stokes equation and then we integrate the Navier-Stokes equation within the volume. So that is what we are doing. So that's where this sign is coming. So in the control volume is so in the smallest scheme of things, it's the cell. Okay, so you integrate the equation within the cell, and you integrate it in the full domain when you integrate from one cell to the next, to the next, to the next. So that's what we do. So and these equations cannot be solved analytically because there are a large number of equations, and we don't have enough equations to analytically solve them because we may not have the same number of unknowns, or the other way around. We have unknowns, we don't have the same number of equations. So therefore you cannot solve it anyway. And what we are doing is we are approximating these equations, the solutions to the equations using a numerical method. So these equations, they define the flow in a continuous fashion, meaning there are no gaps, but in the numerical solution we consider it in a discrete fashion, in the sense we take it as segments. So discrete means that if you have infinite number of discrete elements, so that will become continuous anyway. But that is what we are trying to do. So a continuous domain versus a discrete domain. So this is an example. So that's a continuous domain from 0 to 1. So that's a discrete domain. So from x1 to xn. So this domain is comprised of an ensemble of discrete elements, 1, 2, 3, 4, and so on. Yeah. So if the domain is continuous, we can use partial differential equations and boundary conditions to solve it. But partial differential equations, so the kind of equations that we see in the Navier-Stokes equations. In a discrete domain, we don't use equations, we use algebraic equations, meaning additions, multiplications, and so on. So those are algebraic equations. So the difference between finite difference 1D, finite volume 2D and 3D processes are like this. So we use finite difference in one dimension. So that would be discrete domain divided into a finite difference scheme. And so if you, for example, du over dx plus ui is equal to 0, so that would be a finite difference equation. And then you write an equation for the I minus 1, so that would be ui minus delta x, so delta x would be that length, du over dx plus 0 times delta x squared. So now that would be, so then you write an equation for du over dx I. You take everything else to this side, and you du over dx to the left hand side, and divide everything by delta x, and that would be your, so that is your truncation error. So that is your approximation, the approximation and the truncation error. So meaning this is what you will eliminate from the equation. Yes. So that will be your answer. So likewise, now you have a finite difference equation for a discrete one-dimensional case. So in a 2D case, so this is finite volume method. Finite volume method means you define everything at the cell center, and it has dimensions of delta x times delta y, and then you do a similar thing, meaning what you do is you integrate over the volume. You integrate over the volume, and then again you write an equation. So when you integrate over the volume, you could say ui delta y, u1 delta y, u1 delta y minus v2 delta x, so that is what is going out, plus u3 delta y plus v4 delta x would be equal to 0, so that is coming in should go out. So that's how you So you can have a similar scheme for three-dimensional as well. Yes. So in that case, you will have an z direction. And then we have three definitions what are called discretization, accuracy, and round-off error. So discretization means you write a finite difference scheme in place of a partial differential equation. So that is what you mean by discretization. So you use a discrete scheme. Accuracy is how so then you make an approximation to solve the finite difference scheme. So usually you use a Taylor series scheme. So the difference between the actual Taylor series scheme and the finite difference approximation is leads to the accuracy or inaccuracy is the problem. Then you have the round-off error. So round-off error is is the error that is given to the problem by the computer. That means every number it has a limited number of digits to the number. So it doesn't have infinite digits to a number. So where you truncate that number will lead to the inaccuracy or the round-off error. Okay. So when you look at truncation error, so this is a typical Taylor series expansion. So yi plus 1 could be yi plus hyi plus h square over 2 yi prime and so on. So if we go second order, meaning you have up to here, so your finite difference approximation is only that, and that would be your error. So that is that will lead to the error. What error? Error due to the approximation. Okay? It's not the round off error, or you call it the truncation error. Yeah. So you truncate this equation. Therefore, if for a second order approximation, you will have that as your numerical scheme, and that will be your error. So if, for example, if you have a first order derivative, that means you only take that. So your truncation error would be second order. That means this is the highest element of the error. Okay. So these are first order formulae. For example, yi is xi in the x direction, yi plus 1, yxi plus 1, yi minus 1, yx minus 1. So this is so it's a first order case. So yi plus 1 should be equal to yi plus h times yi plus 1. So and yi minus 1 is yi minus h times yi prime. Yeah. And so if you use a forward differencing scheme, yi plus 1 would be yi plus h yi prime. That would be yi plus 1. Sorry, yi prime would be equal to yi plus 1 minus yi over h. Yes. And backward difference scheme, so that you go backwards, yi minus 1, so that would be here, is equal to yi minus h times yi minus yi prime, and your yi prime would be yi minus yi minus 1 over h. Yeah. So this diagram represents only the forward differencing. So if you want backward differencing, so you will have to have a xi here and xi minus 1 here. Then you have a second order formula. So in the second order formula you have so that second order means you take, so now that's your xi, so you go xi plus 1, xi plus 2, second order. Okay. So to have an approximation for this xi, you will take xi and xi plus 1 and xi plus 2. Okay. So your Taylor series would be yi is equal to yxi, which is yi plus 1 is equal to yxi plus 1, yi minus 1 is yxi plus minus 1. So this is the first order element, and the second order elements are yi plus 2 is equal to yxi plus 2, and yi minus 1 would be yxi minus 2. So your h would be xi plus 1 minus xi. So then you replace these equations. So the Taylor series approximation is yi plus 2 is yi. So if you go back to the Taylor series, that will be your Taylor series. Yes. So that's your full Taylor series, but you use the second order only, that part only. Yeah, for a second order case. So your yi minus 1 and yi minus 2 are written in this form by replacing yi plus 1, yi plus 1 and yi plus 2 in the Taylor series equation. Yes. So that is how you get yi plus 1, yi minus 1 and yi plus minus 2. Yeah. Then you have a second order central difference scheme. So that's your second derivative, yi double prime. So that's your first derivative, yi prime. So you need your yi prime and yi double prime for these equations. So your yi prime and yi double prime are so yi prime is the first order derivative, yi double prime is the second order derivative. Yes, so you derive you get those equations, from the Taylor series expansion equation. And if you go second order forward difference, so that will be a forward difference scheme. So second order second order forward difference scheme, that is for the second order derivative. So that is that will be for the first derivative. Second order scheme for the second derivative, the first order scheme for the first derivative. And if you go second order backward scheme, so that would be your backward scheme. So if you look at these two equations for the forward scheme, so your backward scheme would be minus here. Okay. So but because this is a so you have two minuses, so this will become positive again. So the second order second order backward scheme second derivative would be that. Second order backward scheme first derivative would be that. Yes. So again, if you go back, it all comes from this Taylor series equation. Yeah. And the second order forward difference scheme is that so you will have so that would be your first derivative, second derivative. That would be your first derivative for the second order forward difference, and that is for the second order backward difference. Yeah. So we did that. And for third order formulas, no, sorry. And that is your second order. That will be a second order central difference scheme. Yeah. So in the central difference scheme, you have yi minus 1 and y plus 1 both for the first derivative and the second derivative. That's the first order that's the second order forward difference, second order backward difference. Did I say right? Say this correctly. Yeah, that's the second order central difference. Okay. Yeah. And third order formula. So there is no third order central difference formula. Okay. And but you have Taylor. So if you get the Taylor series expansion, For the third order, you go in the third order you go xi plus 1, xi plus 2 and xi plus 3, so third order. Yes. So in the Taylor series expansion you have a third order as well here. Yeah. So why third prime? No, not the treble prime, triple prime. Yes. So that's your third order forward difference scheme, and for the first derivative, so that would be for the second derivative, and there is one for the third derivative as well, because you are looking at yi triple prime. Okay, so you need to have a yi prime, double prime, triple prime. So that is for the backward differentiating scheme. Actually, there is a typo here, so that would be forward. So then you have the backward differentiating scheme where you have xi minus 1, xi minus 2, xi minus 3. So that will be your first derivative, that will be your second derivative, and that is for your third derivative. Yeah. So that's quite a short lecture. So these are the schemes that you need to know. You don't have to by heart them, but just an open book exam. But you need to know the meaning of these. Yoge, you asked about past papers, so I'll put up some past papers sometime next week or so you can see what is asked in the exam. So
we know what format we're having the exam in?
I think it's 4 questions, answer all.
Sorry, I meant by that, like, even though it's online, are we going to come in and do it, or are we doing it from home?
You can do it online from home. I think.
Yeah. Otherwise, we'll just sort of room out here and we'll come in and do it.
Yeah, still online. Yeah, so, I think it's 4 hours. 2 plus 2.
Just working out whether we should like have notes like printed off and ready to go, or just have like.
You can have it bring your computer.
Yeah, so even if we do it on site, we can have our laptop.
Yeah, open book, so you can have anything you want.
Put 4 hours in.
It's not a very long paper. It's a 25% of the module.
Oh, we have 4 hours.
4 hours altogether. So it's a 2-hour exam. You'll have 4 hours against the exam and you do online. So that's the protocol. So how are you guys doing with the assignment?